for joining us today for this webinar with Mettler Toledo and the title Good pH Measurement Practice. My name is Tina Jüling. I'm a commercial communication specialist at Fisher Scientific, part of Thermo Fisher Scientific. Here at Fisher Scientific, we offer a series of informative webinars to support our customers. These webinars are designed to help you stay updated on our products, improve your knowledge and skills, explore the latest technology, and connect with experts in the field. If you would like to see upcoming webinars or watch previous ones, you can visit our dedicated webinar webpage. Please note this webinar is being recorded and will be available later on our website. And now I would like to hand over to my colleague Eva, who will explain how the Q&A session will work.
Thank you, Tina, and hello everyone, and welcome again to the webinar. My name is Eva Albertsson, and I will guide you through the question and answer session after the presentation. You can ask questions at any time during the webinar. Just type your question in the chat box on the right side of your screen. Our expert will answer your questions during the question and answer session at the end of the presentation. So over to you, Tina.
Thank you, Eva. So now I think we're ready to start with the webinar. Today, we are delighted to be joined by Scott Marsden, Sales Director at Mettler Toledo. Scott lives in Nottingham, UK with his family and has been with Mettler Toledo for 14 years after working at Fisher Scientific. Over the past decade, Scott has visited many laboratories and spoken with hundreds of customers about their pH meters and electrodes. He has supported them in choosing the right electrode, using it correctly, and when needed, troubleshoot when things go wrong. So I will now hand over to you, Scott, and hope you all enjoy an interesting and informative webinar.
Hello, thank you very much for that wonderful introduction. So as I said, my name is Scott and I work for Mettler Toledo, and today we're going to go through good pH measurement practice. So as part of our agenda, we're going to be looking at what is pH, why we measure pH. Then we're going to go through some details about measurement principle, probably the most difficult part of the slides. Then we'll go through calibration and adjustment, something about measurement uncertainty, using meters and operators, pH sensors and solutions, and then measurement practice. And then at the end, we have a quick wrap up and questions and answers if we need them. So the first bit is what is pH? So pH is a chemical property of a solution indicating the degree of acidity or alkalinity. So we're measuring the acidity or alkalinity of a solution. We have acidic solutions that are bitter or sour. So for example, lemon juice with citric acid. There's phosphoric acid in Coca-Cola, but you don't taste it because of the sugar. And then there's alkaline solutions that are caustic and feel like salt water. So when we're talking about acids and bases or acids and alkalines, what we get is an acid and base dissociating in water. So when we had something like hydrochloric acid, they break down into hydronium plus ions and chloride ions in the water. And the amount of these hydronium H plus or H3O plus ions or of the OH minus ions are a measurement of our pH. And this again is a bit more in depth. So when we're using this, we're using a solvent is water. It doesn't always have to be water, but 99% of the time it is water. And we use that as an acid and base and produce these hydronium H3O plus ions and hydroxide ions. Also, whilst we're doing this kind of bases and reactions, we also have a dissociation constant, which is driven by temperature. So as you go through these slides, we'll see temperature is really important when we're measuring pH because it affects lots of different things, including this dissociation and then lots of other things as we go further down. So how do we measure pH, or what do we measure it in? We measure it as a value, and that value is a number from 1 to, well, actually 0 to 14. You can get negative numbers and you can get above 20 if you're not in water, but generally it's between 1 and 14. And for that, what you do is we measure the inverse logarithm of the H plus ion content. So when we've got 10 to the minus 1, which is very high morality of H plus ions, we are talking pH 1. And so on and so forth as we go. And each time we are decreasing, each time we decrease down the scale, we're timesing the solution by 10 times more acidity, basically. And when we look at this in tabular form, you can see here, we've got pH 1, which is an H plus ion or hydronium ion concentration of 0.1 down to 0.7 and then 14. So, and it kind of gives you the difference between the H plus ions and then the hydronium ions at this side as well. So it really is a measurement there between 0 and 14. Then if we look at the scale itself going from 0 to 14, you can see most common household products that you see: lemon juice, Coca-Cola, orange juice, all the way through to egg whites and borax. And then in the bottom, the most common things you would find in your labs. So sulfuric acids, acetic acids, ammonia solutions, all these different ones all have a pH scale somewhere on this pH scale, depending on what the product is. So we found out what pH is. Why would we measure pH? pH, in actual fact, is the 5th most common measured parameter in the laboratory after temperature, time, volume, and mass. And after that, then we're talking pH. So after all those, pH is the 5th most measured in the laboratory. And why do we measure it? Well, pH values characterize a product. They can influence the development of biological habitats. If you've got a river and you pour acid into the river, chances are you're going to kill something in that river. But biological habitats might also be a petri dish. You're growing some cells in a petri dish, and inside that cell is the pH is wrong, and you're going to kill those. It influences the shelf life of pharmaceuticals, chemical reactions, the properties of oil. If you are old enough to have an old car that still uses oil instead of a battery, you'll realize the oil inside, if we had an acidic oil, it would corrode the engine. Also, car batteries isn't in this list, but is a big now place where we use and measure pH. Cosmetics, you won't want to put something too acidic on your skin. And then also there is a whole load of laws and regulations around pH values. So for example, there's a law around the pH of milk before you can sell and use milk for other products. So there's lots of different areas there. And then what kind of applications? So drinking waters, food and beverage industries, farm industries, cosmetic industries, education, universities, medical applications, biological processes. All of you on this call will all be handling or be working in some of these areas already. And the reason why you're using that pH right now. So we've done what is pH and why we measure it. The next bit is how do we actually measure the pH values? So here, what we're going to talk about is exactly how a pH meter and electrode, particularly is the electrode is more important, how that works in a system and how it produces a pH result for us. So when we're measuring pH, what we do is we measure it by potentiometry. Okay, and basically what we have is a pH meter that is a voltmeter, measuring voltages. And it doesn't matter if you buy a relatively low value pH meter or a test stick, or if you spend thousands of euros or pounds on a pH meter itself. They all do exactly the same job, and that is take a voltage. Okay, and what we're doing is when we're doing this and we're taking this potentiometer, we're measuring the difference between a reference electrode, which you can see here, and a measuring electrode, which you can see here. And the difference between those two the potential difference between them both gives us a measurement reading. Okay, all of this is in a circuit, and that circuit is provided by the solution. So we're in a solution itself. So we're in a solution here, and then this electrode is doing one job, and the measuring electrode is doing another. So what we're going to do is we're going to take a look at each one of these electrodes and find out why it's important, and then what we can do and why we look after them and take care of them. So the first one is the reference potential. Okay, so this reference electrode here, we're trying to get a single steady constant reading from this signal. Okay, and what we do is we have a silver chloride system. Now, for Mettler Toledo, we only use silver chloride systems. We don't use anything else at the moment. However, you do get other systems as well. Some old ones used to be mercury. So you used to get mercury or calomel ones, but they're less common nowadays, but you do get some other systems. But particularly we use a silver chloride one. The systems kind of all work in the same way. What you've got is a silver wire with some silver chloride coating on it. You have an electrolyte inside, and then you have a junction, and your sample is coming to contact in this junction area at the bottom. And what we want from this reference electrode is we want the electrolyte in here to flow out into our sample. So when this electrolyte flows and the ions flow out of here into our sample, it pulls ions off this silver chloride coating and it generates a reading. And so the most important things here are the electrolyte inside is clean and constant and always the same. And then this junction at the bottom has to be open and clear and usable. So once we've got a reference electrode, the next part was our measuring electrode. And here is our measuring electrode, and the measuring electrode measures the potential across a pH-sensitive glass. So what we've got here in the tip of our bulb, and this is normally our glass bulb at the end of our measuring electrode, what we have is we have a lovely piece of glass, and this glass allows the transfer of H+ ions in and out of the glass. Okay? And here you can see the glass, and inside this glass is a buffer that we can't touch or use, it's sealed. And then on the outside of our bulb, our glass bulb, we have this gel layer. And this gel layer is full of hydronium ions ready. So it's full of those H+ ions ready to go. And what happens is if we have an acidic solution, those H+ ions flow in and cause a positive charge. And if they are we're in an alkaline solution, they flow out and into our solution and cause a negative charge. Okay, and once we've got this charge, this is our measuring charge. Now, the really important thing here is when we're talking about the measuring bulb is obviously this glass here, this gel layer on the glass has to be absolutely clean. It has to be well adhered to the glass, and it has to be full of H+ ions ready. So if this is broken away from the glass, or it doesn't have the hydronium ions ready or the H+ ions ready to go, it's not going to work. So one of the really good techniques is if you go back to your labs today, as soon as we finish this webinar, you can go and take a look at your electrode and you pick it up and you look at the glass bulb end. What you'll find is the glass bulb end is normally a different color. So it's really hard to show on the webinar, but if you actually take a look, normally it's tinted green or it's tinted yellow or maybe a little blue sometimes. And that is the actual gel layer. And that's the reason why the glass looks a slightly different tint of color to the rest of the normal glass electrode. That's because you've got this lovely gel layer on it. The next bit is, and the most common question I get from that is, well, when I'm using pH, I've only sticking one electrode in. And that's because due to advanced techniques and manufacturing techniques, we're able to take the measuring electrode, the reference electrode, and shove them into one electrode. And we call this generally a combination electrode. So sometimes when you see it, you might see, oh, it says combination electrode. And that's because we've taken both electrodes, pushed them together into one piece. So here you can see in this diagram, you can see the outer glass bit here. This outer glass is the reference part, and it's full of electrolyte inside. It has a little junction here that you might be able to see in the picture if you're looking. And then in the center, you can see this second piece in the middle, and that pops out at the end, and this is the measuring part. So you can see this glass is ever slightly tinged yellow, whereas this is clear glass. This is slightly yellow, where we've got this pH-sensitive glass membrane, and it's covered in a gel, and then it shoots up in the middle of the electrode there. So when we see combination electrodes, that's what we mean. We mean we've just put them both together. However, most electrodes in most occasions nowadays, for 90%, 95% of measurements, are done with combination electrodes. So the last little bit of what we did is a couple of slides back, I showed you just quickly. This part here is said where we measure the potential difference between these two electrodes. It isn't straightforward maths as minusing one from the other. What we actually have is we have another part of the equation that's shoved in, and it's called the Nernst equation. And this bit takes the measured and the reference potential that I've just talked about, but it also adds a universal gas constant, and a temperature and a Faraday constant. And basically, if we take this equation and put it all together, it gives us what we see as a measured potential as a voltage compared to its pH. So we actually get the logarithm of the pH. So in reality, hopefully, when it's theoretical behavior, when we shove and put our electrode inside a sample, it should reach pH 7. It should say 0 millivolts. And then for every pH we go up or down the scale, we're changing it by 59.16 millivolts either way. So if it's pH 6, it's going to read 59.16, and if it's pH 8, it's going to read minus 59.16. And that is all due to this nearest equation. Yet again, it's got temperature in there. So it's really important when you take pH measurements, you write down the temperature, because if you want somebody to repeat that result or to look at that result, they're going to need the temperature along with the pH in order to be able to process that. So something really important to think about. So the next problem is we all work in the lab, and we all know that in real life, nothing ever happens as it's meant to in theoretical behavior. So when we're actually taking a measurement, what happens is we've got the whole system, we've got the electrode, we've got the wire in between, we've got the buffers to do calibration, we've got all sorts of different things going on. And in actual fact, when we come down to it, this is the theoretical behavior as we think it should be, and then we get something that's called the real behavior. And the next bit of the slides is how we can compensate for that real behavior. And that is through calibration and adjustment. So when we're doing calibration, we normally say we want to calibrate the pH meter. In reality, we're not actually just calibrating the pH meter, we're also adjusting that curve so that we're adjusting for the real behavior that's going on in our labs. Okay, and the calibration is, we know what our calibrants are, we know what our pH buffers are going to be because it's written on the bottle. And the pH meter may, hopefully, in the case of Mettler Toledo, it is programmed and pre-programmed into the meter. So when we come to use our buffers, it can adjust to the real behavior that's happening in our system between the electrode, the wires, the buffers, and the meter itself. So when we actually do a calibration, we're doing a calibration followed by adjustment, even though we just say we're calibrating the meter. But in reality, we're making that adjustment too. So the first thing we do is we use a known buffer. So in this case, we're using pH 7. And what we do is we plop it in and take our calibration. And what it does is it corrects the curve by giving us an offset. So this offset is 10 millivolts. So either 10 millivolts to the left or up, and it moves by 10 millivolts away. So we know our pH 7 should be 0, but when we've put it in and taken a measurement, it actually reads 10 millivolts. The next bit is we then use a second one to give us a slope. So we've got a 2-point adjustment here now, and this slope has moved. So once we've done this, we've given an offset and then a slope. And this slope, we were meant to have 59.16, which is what I had on the slides before. But in reality, we've actually got 58.9. Okay, and when we do this, normally in meters, we normally write it as a percentage. So in this case, the difference between these two is about 0.5%. So it would be 99.5%. And that's generally how it's written in a pH meter. When it comes up, it'll give you the slope and then the offset as a percentage. And that's basically what we're doing when we're calibrating. The next bit for calibration is about linear and segmented. So when we're doing a 2-point, we can only draw one line of best fit between the 2 points. When we've got a 3-point calibration, we can do something called segmented. So instead of drawing a line of best fit, we can actually draw one line between points 4 and 7 in this case, and another line between 7 and 9. And if we're taking a measurement at, say, pH 8, it would take this line. And if we're taking a pH measurement at 5, it would use this line instead. What this does is it gives us a really more accurate calculation of what's happening with the real behavior. Because yet again, in the theoretical behavior, we say, oh, it's just one big straight line. But in reality, it never works like that. And therefore, we have this calculation. And you can use that in some meters. So yeah, again, the Mettler meters for the 7 direct and 9 focus do what we call a segmented calibration. And some of the 5+ series as well do segmented. It offers more accuracy afterwards for your pH measurements when you come to them. That's a bit on calibration adjustment. I'm going to go back through when we go on to pH sensors and solutions. I'll go back through calibration again, talking about buffers, how to use them and what to do, but I'll leave it there for calibration about, because it's more about the principle of calibration than it is about the actual physical doing of it. And then we'll go through it in a second. The next part we've got is measurement uncertainty. So we've got our pH meter. We know what pH is and why we're measuring it. We understand how our electrodes are working and how that fits into the system. We know how to calibrate the system. The next thing is to take a measurement. And this is the point where we need to make sure we're taking accurate measurements, accurate and precise measurement readings in order to get an absolute result that we need. So when we look here, we talk about two things. We talk about accuracy. So when we're measuring the pH in a lab, what we're trying to do is take a measurement accuracy as accurate as we possibly can. Now, when we're doing this, because of all the different parts that we've got into our system, that includes the buffers, the electrode, the wire connecting the two, the meter itself, by the time we put all those into account, then what we have is we have what we call a measurement of uncertainty, okay? And if you're in the best lab in the world with the best measurement, you've listened to my slides and you think they're wonderful and you do everything that I say all the time, and everybody in your lab does it as well. And you take care of everything. You've got the freshest electrodes with the newest high-angled meter. Realistically in your lab, the best you're probably going to get is somewhere between 0.02 and 0.05 pH. So if you can repeat a result at 0.05 and keep repeating that result with the same product over and over again, then you've done a really, really good job. Okay. If you're struggling to do now in a lab, it may be that you don't need to be that accurate. We have a list of 103 people here all listening. So I don't know if you're in a pharma lab and you need to be down at 0.05, or if you're in a food lab where plus or minus 0.1 of a pH might be enough. So it really depends on kind of what your accuracy needs to be in the lab and how you need to take control of it. The last thing is when we're selling pH meters, we're very good at marketing pH meters and saying, the meter itself will read down to 3 decimal places. But in reality, with the system and everything else involved, although we can take that 3rd decimal place as a reading via millivoltage, actually making that last decimal place repeatable is not possible because of the accuracies and the types of influences we have in the system already. So even though you buy a 3-place pH meter, it's only ever going to read at best, repeatability wise, down to plus or minus 0.05 of a pH. So then what we want to do is once we're accurate, what we want to do is make sure we're precise and accurate at the same time. So being precise is getting the same measurement over and over again, but what we want to do is make sure it's accurate. And this is all dependent on you and your sample, the way you handle the sample, the environment, the meters, the sensors themselves, precision studies and everything else. So the more of these techniques that I'm showing you today, or the more of the things that I'm going to show you in a few minutes that you follow, the more likely you are going to be able to be accurate and precision whilst you're taking measurements. Some of them, you might think, that's way too much for our lab. We can't cope with that. That's fine. But then you've got to know that that might affect our accuracy and precision going forward. And you might want to think about those things when you're taking measurements. I've got 2 examples here of some uncertainty in the systems already. So we gave a big long list, but one of these is calibration buffers. So when you're using buffers, you go back to your labs this afternoon and go and look at the bottle or the sachet, you'll find that there's actually a plus or minus of a pH involved in buffers. So even when we're taking measurements with buffers, if your buffer has that uncertainty of, say, 0.02, then you're already introducing that kind of buffer error into your system and into your measurements already before you've even started. The same with temperature. So using different temperatures, each sample and solutions have their own different temperatures. Now for buffers, we know what they are. because we've well measured them. And these tables are actually in our Mettler Toledo meters and in other brands of meters as well. But these buffer tables are pre-programmed in, so you know what the dependence temperature is. But on samples, for example, hydrochloric acid, or for this one, sodium hydroxide, you've no idea. It really depends on what's happening. So yet again, another measurement uncertainty you need to think about when taking measurements as well. Another one is slope changes with temperature. So I originally showed you the Nernst equation where it has a temperature involved in it. So this is going to absolutely change the slope at which we take measurements. And yet again, pH meters, modern pH meters normally take this into account, but it's worth checking that your pH meter does. So in the Mettler meters they do, but in other meters they may not. So the things you need to think about when you're doing that and taking into account this temperature. And that again is why it's really important that we record the temperature when we take a pH measurement. So the next bits and the next 3 chapters are all now about things that we can do in the lab or you can do in the lab in order to help improve and get a more accurate and precise measurement and reduce those measurement uncertainties. So the first one is the meter and the operator. So the first thing is when we buy a pH meter, so we've got a pH meter either in the lab now or we're going to buy a new one hopefully, the first thing we need to do is make sure that we put it in the correct place. So when we're using it in the lab, we need to make sure that the meter and the system itself is at appropriate temperature. We minimize any temperature fluctuations. It's at appropriate humidity. We've got no strong airflow. And then a really important one is we've got enough working space. So the amount of times, as I said, I've been to hundreds of laboratories, talking to lots and lots of different customers. And the amount of times I've been to a lab and the pH meter is on a little space about this big, and I'm trying to do some calibration or measurements and I'm knocking things over. And this happens quite a lot when you've got such a small working space. So something to think about, make sure you've got lots of space around so you can handle those buffers and liquids without causing accidents. The next one we're doing right now, and that is training. So for training, obviously we're training you now, and you can go and train other people. We also do extra trainings. If you need to contact your local fisherette to do face-to-face trainings, we can do that as well. But once you've learned this and learn about these topics, then you can pass it on and make sure that people are doing these kind of techniques, making sure they're correctly handling the system, make sure they understand the possibilities and limits of the measuring system. Like I say, 0.02 of a pH, for example, all these different questions. And if people understand that and trained up, then they can recognize those things. The next one is settings on the meter. So we bought this, or we have this wonderful meter in your lab. I'm presuming not many of you have actually read the instruction manuals, but maybe something to do is to read the instruction manuals. On there, the instruction manuals might have things about calibration settings. Have we selected the right buffer groups for calibration? Has it got different buffer groups we can use, or can we program our own buffer groups in? Which general settings? What's the endpoint criteria? How do we capture the temperature? Measurement settings, so which unit, how many decimal places are we measuring? Then we've got peripherals like stirrers, printers, sample changers, lots of different things there with the pH system that we need to look at and make sure the settings are correct for when we start using the pH meter. So we've got our meter, we know we set it up right. We'll make sure that everything's turned on correctly and everything's sorted. And the next bit is for pH sensors and solutions. So this one is all about our different sensors and how sensors we look after them, take care of them, and which solutions we choose and why. So the first one, and probably another really common question I get, is how long does a pH electrode last? So the lifetime of a pH electrode, when stored appropriately and suitably maintained and measured in aqueous solutions at a pH between 1 and 12, we should expect an electrode to last anywhere between 1 and 3 years. So if you have an electrode over 3 years, it's probably too old and needs looking at. The other thing is that if we're using something like high temperatures, then that would degrade significantly. So down to 3 to 9 months or a few weeks at 120 degrees. The other thing is if we're not doing any of those 4 things above, so we're not storing it properly, we're not maintaining it properly, and we're not measuring aqueous solutions, that will also degrade the electrode life. So things to think about when we're using electrodes is how we use them and how we take care of them. So the first thing is storing our pH electrode. So when we're storing our pH electrode, what we're trying to do here is we're trying to ensure that that gel layer that we had on the bottom of the electrode on the bulb remains hydrated and iron rich. So what we do is we can store it in special storage solution. So you can find some from Mettler Toledo and other brands as well that have special storage solutions. Then when we've done this storage solution, if you don't have special storage solution, the next one is the electrolyte solution that's inside. So the inside here was the electrolyte, and we should store it in that electrolyte. Generally, that is 3 molar potassium chloride. We can store it in buffer solution, so 4 or 7 pH buffer. We can do that as well if need be. And the other one is hydrochloric acid. So hydrochloric acid, 0.1 molar as well. And you could do that a lot of time to clean it as well. And we'll go through about trying to clean it and everything else. So things we never do. We never store the electrode dry. If we store it dry, what happens is that gel layer at the bottom here, on the end of the bulb, that becomes dried, it shrinks and then pulls away from the glass. So if it pulls away from the glass, you don't have the contact to allow the hydronium ions in and out. So we must make sure that we store it as wet or as hydrated all the time. So in some sort of solution. The second one is we never use distilled water. So if we use distilled water here, what will happen is the hydronium ions inside here will leach out, and then it's very difficult to get them back in again and keep it iron rich to allow the flow of ions in and out. So when this becomes depleted, then it won't work. So what we need to do is make sure that we're using one of these recommended storage solutions. At worst, table salt in some tap water would be better than nothing. Then I would go and highly recommend you get hold of one of these solutions if you don't have one in the lab already. But never ever store it dry, never ever in distilled water. So once we know how to store it, the next thing is the electrolyte inside the sensor itself. So the electrolyte, we said, when we're taking a reference reading, we want it to remain constant and steady, in which case we must have a constant electrolyte inside. Okay, now these can be either gel-based or liquid-based. If it's gel-based electrolyte, then we don't need to do anything. The gel in there is stable, it's not going anywhere, and we're absolutely fine to leave it alone. However, if we're using a liquid electrolyte, then what we will need to do is we will need to empty and clean that electrolyte on a regular basis. So what we must do is we must empty and refill that electrode. So we're not topping the electrode up with some new electrolyte, we need to empty it. The reason is because when we start and we use 3 molar potassium chloride, if it evaporates or crystallizes inside, it becomes 4 or 5 molar. Then we top it up with 3 molar, so it becomes 4 molar. And then it goes down again to 6, and then we top it up again. And basically what we're doing is we're hypersaturating that solution with potassium chloride. So we always empty and clean it. We should do this regularly. So we should be doing this once a month. So once a month, we should empty that electrolyte out and refill it again. We can use a little plastic pipette is one of the best ideas, and you can turn the electrode upside down and just suck it out of the little hole that's there and then replace it again. If we get any crystallized in there, then we should refresh with fresh solution, dissolve the crystals and empty and refill again. Because obviously we want to keep that same constant concentration. If we dissolve crystals in there, that's going to change the concentration. So dissolve the crystals, empty it and replace it again. You can also use a little bit of warm electrolyte, so 40 degrees electrolyte, to try and wash it out as well. If there's lots of crystals in there, it's hard to dissolve. But don't use anything too hot because we don't want to, yet again, stress the electrode. Once we've done that, we just give it a quick flick like a thermometer, and basically what we get is we get rid of all the bubbles inside and it's ready for measurement. The other thing is if we do refill it, we've got to make sure that we refill above our level of sample. Because if we go below here, we'll end up sample coming into our electrolyte, which we don't want. We want to keep the level high to keep the pressure high. The next one is sensor cleaning. So we've got the right sensor, we know the electrolyte is good inside, we're storing it correctly. The next thing we need to do is clean it. So in between samples, what we do is we quickly rinse with distilled water, we dip it and dab it dry with a paper towel. We never rub, because if we rub, we cause electrostatic, and that electrostatic can stop the flow of electrolytes and ions. So we never rub, we just lightly dab the electrode in order to get rid of any excess solutions. If we're using something non-aqueous or dirty, we can wash with a solvent to get rid of dirt, but we must immediately wash with distilled water and get it back into some sort of conditioning solution, back into storage solution or whatever else, because we don't want that electrode to dry out. Yeah, again, if it dries out, that layer of gel shrinks and cracks, and we don't want that. So, after we've done that, we now got a clean electrode, we're ready to go. Before we take our first measurement, we need to do this calibration and adjustment. So, what we do is we must calibrate our pH meters at least once a day. So, it may be yet again down to your SOP. If you're using your pH meter every day, you should calibrate it. If you use it once a week, then you should calibrate it before you start using it. If you have some regulations or SOPs where you must calibrate after every batch, then obviously you need to do it after every batch. We should be performing at least a 2-point calibration. The more calibration points we've got and the more segmented it is, the more accurate our measurements are going to be. But we should have at least 2, if not 3 points. And yet again, we should try to make sure that we calibrate at the same temperature we're taking our readings. That will help with this measurement uncertainty. If we calibrate hot and then measure hot, we calibrate cold, we measure cold. We do it at room temperature, then we calibrate at room temperature. We should always use fresh buffers, so we need to make sure we're using accurate calibration buffers for accurate measurements. And then the possible errors there are we're not doing it frequently enough, so make sure you're doing it at least once a day. Make sure you're doing it at the right temperatures, and then making sure you've got the correct buffers. We've got some more slides on buffers. So when we're using buffers and buffer handling, what we should do is we should make sure we look at the expiry dates. So this is a picture of the Mettler bottles with an expiry date on, but you should always check the expiry dates, make sure they're in. Once they're opened, write the date of opening on the bottle so you know how long that bottle's been open for. The other thing we do is we never calibrate inside that bottle. We always take buffer solutions out into a smaller bottle and then measure into a small capsule or a small bottle, never directly into the solution. The other thing is we never keep that little bit. So once we take a pH measurement, a calibration and adjustment, once we've used that buffer, we throw it away. Okay, because that little piece can become contaminated. So what happens is we take the buffer measurement, we throw it away. The next time we do a buffer, we decant some fresh solution and use the fresh solution and then throw it away. So we're using it all the time. And that's really important to keep the measurements accurate, keep the calibration accurate. And another one to use is consider using single buffer sachets, because the single-use buffer sachets are really good at making sure that you have an accurate pH calibration all the time instead of bottles. So it might be something you want to consider longer term. And yet again, Mettler offer a range of these that I'll show you in a second. So here you can see a range of bottles, and then these are the single-use sachets on this side that you can see. We do a different range, so you can find lots of different buffers. So you've got to be really careful about which ones you select. At Mettler Toledo, we offer a technical buffer. So that has a calibration. You'll see it, and it has a certificate to say, or a verification certificate to say, this is the pH we've tested it at, which is fine. You may be in an accredited laboratory where you need to take account of accredited buffers. So we do a range of DACAS certified buffers. They are independently tested by a separate laboratory and come with the ISO 17025 accreditation laboratory confirming its certification. The other ones we do our NIST and DIN buffers. So it depends on what kind of measurements and what kind of system to use, but we also do NIST and DIN buffers in bottles and sachets. This is more about single-use sachets. So it shows you here, we have dispensers here showing them off. They're available in packs of 10 or 30, depending on what you need to do. But what this really does is it really improves your accuracy when you're taking calibrations, because it's sealed inside there and it's a single use, and when it's done, it's thrown away as well. So this is a list of everything we've got. So different values, and then the uncertainty here you can see is plus or minus 0.02 we talked about before, and then Different ones have different shelf lives depending on what there is. So then when we do a calibration, what we then get, so we've taken our system, we've stored an electrode correctly, we've made sure it's clean, ready to go, we've taken a calibration, an offset, an adjustment, and here's what's happening here. So we've done a sensor calibration, and it goes back through this offset and calibration slope. So here you can see this is the designation that at Mettler Toledo we decide is a good or a bad calibration. So if it's between plus or minus 0.5% and 0 to 20 millivolts, we say everything's good and everything's great. And in our meters, you will see a little symbol that shows like a telephone signal with 3 bars. And these 3 bars on our meter actually are showing this type of thing. So it's really important that you understand when you've taken a calibration, if it's good calibration or a bad calibration. Now here we say the sensor's in good condition or bad condition. This is only correct if your pH buffers are correct. So now we're presuming that you've taken care of your buffers, you've got the right buffers. And if that is the case, then these slopes are correct. And if you're getting something that's way out of slope or offset, then either your sensor's defective or old. And you need to make some fixes to the electrode, which we'll go through now, or you need a new electrode to replace. So if something is wrong with our electrode, we have some cleaning solutions here. So if we've got silver chloride or sulfide, we can use ammonia or thiourea to clean it. Another really popular one, lots of people do in life science biological habitats using proteins. They need to clean with 5% pepsin. And then there's other junction blockages. We can use an ultrasonic bath. So if you use an ultrasonic bath, we can try and wobble blockages out of that membrane or junction and make sure it's clear, ready to use. Okay, once we've done this and treated an electrode, we must rinse, clean, and then perform a new calibration. So yet again, anything we do to clean the electrode, we must perform a calibration afterwards to make sure. For the lifetime of the sensor, obviously, yet again, we do storage solutions, we do pepsin solutions, all those different things to try and keep it ready. So there are things you can look at in the Fisher catalogue, and there's full of solutions there that you can use as well to keep your electrode in the best condition. The next one is looking after this gel membrane. So if the gel membrane dries out, so what happens is if we get unstable readings or we can't get stable readings, then that's caused by dry membranes. And that could be caused by either we have non-aqueous solutions, or we've used iron deficient media, we've used the wrong storage, or an old sensor as well. So when we talk about old sensors, what we mean is this gel layer has a lifetime. This gel layer eventually gets loose and flaccid. Over time, it just dissolves away, and eventually it will get old and just wear out and not function the way it's meant to. And that's just life, that's just normal life of an electrode. So when we came at the beginning of this 1 to 3 years, it's generally around that gel layer that's on. So if we have reduced sensitivity of glass and it's washed out and we have unstable readings, then what we can do is we can try and condition in this hydrochloric acid. So 0.1 molar hydrochloric acid for 12 hours. That's a really good one for cleaning electrodes. And I would recommend, if I'm in a lab, for once a month for you to run this conditioning. Whether your electrode's in good or bad condition, it just helps. It keeps it well hydrated and full of those H+ ions, that gel layer. So my recommendation is condition once a month, whether your electrode is old or new or anything else. And then a reactivation solution can be used, which is a light hydrofluoric acid that sometimes can correct it as well. Obviously, if none of these things work, then the only thing to do, and it's an old electrode, is to replace the electrode. So hopefully that's helped you take care of the electrodes, choosing the right buffers and solutions as well. The next one is just how to take a measurement. So when we're taking a measurement, we've calibrated, everything's ready to go. So we start taking our first measurement. The first thing we need to do is make sure our sample is homogeneous. So that means everything's well mixed. So we might need to stir our sample first. Not with the electrode. We don't stir samples with the electrode like this. What we do instead is we use a stirrer. Now, when we're taking measurements, we generally don't want to stir, because we stir, what happens is we introduce air into our sample, and that air in our sample can make it can introduce other things like carbon dioxide from the air, for example. So we need to switch off and then take a measurement. Some methods, the DIN method, for example, requires stirring. So if we are going to do that, we need to make sure the stirring is at a low volume. It's not mixing or swirling the sample, yet again, to stop that air. Next one is making sure we've got the right temperature. So every sample has a characteristic temperature. Knowing and measuring the temperature is key for pH measurements. So lots of our electrodes have temperature sensors built in, like this one, the Power Pro has an integrated temperature. And it's really good to make sure that the temperature is known, is well constant. And if you can't do that with an integrated temperature sensor, then you should measure the temperature and type it into your pH meter as you're taking those pH measurements. If we've got very, very small samples, that's really difficult. And especially when we've got electrodes like this one, this is the Ultra Micro Pro for measuring very small samples. If we do need to do that, then the best thing to do is to heat the electrode to the same temperature as you're taking your sample. At room temperature, that's not a problem. But say, for example, these tubes are at 37 degrees, then if you introduce your electrode at room temperature, it would change the temperature of your sample. So what you need to do is you need to heat your electrode in some storage solution at 37 degrees. So when you introduce the electrode into a very small sample, they're both reading the same reading. So it's something to take account of when you're taking temperature measurements with very small samples. And then when we're taking measurements, there's just some things to remember, making sure that the temperature is stable. That electrolyte level we talked about before, and the electrolyte level is high here. Making sure your junction is completely submerged. So make sure that is in the sample as well as your bulb. Make sure your sample is homogeneous. And then if you do have an a liquid electrolyte, then it's really important you open this hole, because this hole can cause a vacuum inside the electrolyte if it's not opened. So during measurement, you open it and then you close it again when measurement's finished. Something to remember. Okay, so that hopefully wraps up nearly everything today. The only thing I've got left is, during this talk, I've talked about lots of different things, and you may not remember them all, which is absolutely fine because that happens. But what we do have is Fisher Scientific have a really good web page branded with Mettler Toledo with all this different information on. And so on here are the links. So there's 7 different links, and they all link back to Fisher's website. If you just give me a second. And here you can see the website for Mettler Toledo's landing page, and it has our products and our featured products, which is brilliant. But then it has some related resources. So some really good ones here are the pH theory guide, and that is a lot about things we've talked about today. And then pH essentials is all about cleaning those electrodes and things. We also have an applications page. So all about this cleaning and looking after electrodes is done in video format. So you can see those here. I won't play the videos now, but you can go and look at them. And then there's also practical application guides for each of your types of measurement. So some of you may be in a pharmaceutical lab and you might find applications here. Some of you are in food labs and you can download them, using jams or chili or meat and things. And there's beverages and conductivity. So really good libraries there. And then there's also ones about using our meters. So how to set up our meters, how to use our meters, and on buffers and solutions as well. So some really good stuff there. And then the last bit is the resources. There are lots of different resources here. Most asked questions, things you might want to download for your lab and share with your lab, expert tips, calibration guides as well. So lots of different techniques there too. So if you need any of those, please let us know. And from my side, that is everything. It's just down to questions, I think, now.
Thank you very much, Scott, for a very nice presentation. So now we will move on to a few questions from the audience. And it was very good that you show our homepage. We have a lot of stuff there, because the first question we have from Eric, can I have this presentation in a book? But I think you already answered that now in the end, to show what we have in our homepage and also in the Mettler Toledo homepage. Mm-hmm. So you have it all there, I think. Yeah. Then we have also a question about different languages. I don't know, Scott, if everything is available in French or Spanish.
My language is restricted to English.
Yeah,
However,
okay.
However, we do have representatives across Europe who would be quite happy to help and do individual trainings in different languages. So the best thing to do there is probably to contact your local fisher representative, and if they do that, they'll be able to contact the local Mettler Toledo representative in that country. So I have a team, or we have a team at Mettler Toledo in each of those countries. So if you go to your local fisher representative, ask them, and I'm pretty sure something can be arranged locally within that local language if need be.
Excellent. Then we have the first question about electrodes, and it's Andreas who asked, how about autoclavable electrodes? Can you do that? Autoclavable?
Yes, you can. I have to remember, I think our Power Pro ISM electrode goes up to a temperature above 120 degrees and is autoclavable. I would have to go and check just to make sure on that one, but I think one or two of electrodes are autoclavable. But I will it's something I need to note, and I will come back on that one.
Yeah, and also Andreas asking lifetime, I mean, with autoclavable electrodes, but then you have to come back.
Yeah, again, we're exposing them to very high temperatures, so the lifetime would be dramatically reduced because you're going to affect that gel layer. You're going to virtually dissolve it with the temperature. So yeah, again, if you have to autoclave them, because you might have to, the lifetime of those electrodes is going to be reduced because they've been autoclaved.
Mashad has a question about, what about a very small pH electrode? How long can we use them?
Yeah, so they should have the same lifetime as a normal electrode. Just because they're smaller, as long as you're taking care of them and in the same care that you use on a big electrode, they should last the same length of time. We at Mettler Toledo do a range of really small ones. And yet again, on that Fisher page, there's some application guides of using very, very small samples. And we have something called an Ultra Micro Pro, and you can use that in a 96 well plate. And so that is very, very small volumes in a 96 well plate using an electrode. The only thing there you've got to watch is, I mentioned it in my slides, is the temperature. So you've got to make sure that electrode is the same temperature as your sample before you take measurements. So the sample isn't heated or cooled by your electrode. But apart from that, yes, we do very small ones and they should last just as long.
Then we have a question from Rose. How can we do for electrode without refill system? And I think it was when you were talking about how to treat your electrode, this question come up.
Yeah. So I'm presuming this is to do with the electrolyte inside the electrode, so whether it's refillable or not. So some electrodes you just can't refill. They are generally filled with a gel. And if you can see inside them, you can't see inside all electrodes, but if you can see inside them, you'll see it's a gel layer or a fixed gel that doesn't move. If it's liquid, it should have a cap at the top that you can open and refill. So that is how to tell if it's got a liquid one, because it should have a little filling hole at the top so you can empty it and refill it and keep that electrolyte fresh. But if you have a gel one, then that works. The gel absolutely fine. You don't need to refill it or take care of it. Now, a little bit about gel and liquid ones is why you would choose one over the other. The main advantage for the gel one is you don't have to do anything with it. You don't have to take care of it. It's virtually maintenance free. However, gels don't work for all samples. So, for example, they work in a liquid sample, but if you add a gel and a very viscous sample, then that's not going to work because the transfer of ions is too long and takes too long. So that's where you'd have to use a liquid filled one. But if you can get away with a gel one, I would choose a gel one all day, every day, because you know that you don't need to take the maintenance of it. But if you have to use liquid because your sample's, like say, thicker, or you've got some use for that, or it's got to be special, then a liquid one, you just got to remember to refill and take care of it.
Okay. And we have from Amisha again, are the separate electrodes designed for solid and liquid food samples?
Yes. Yeah, again, we have a range of different electrodes. I think there's over 90 odd different Mettler pH electrodes in the range, so you can go and take a look. And one of them is what we call a Solids Pro, or a Solids Pro ISM. And this is a puncture electrode, so it's a glass electrode, it's gel filled, and it has a little tip, like not sharp, but like almost like a conical tip, and that is for puncturing meat, cheese, solid samples, semi-solid samples like agar, for example, and you could use them in solid samples as long as the solid is a moist sample to take a measurement. We also do surface ones, so if you want to take the surface for things like agar plates and you want to take a measurement of the surface pH, we also do surface electrodes as well. So we do, a big range of electrodes covering lots of different ones. And you can find all of those either on the Fisher website or in that link for the different electrodes and applications.
Great. There are solutions for all kinds of applications, I hear.
Yeah.
So, next question. Keely asking you if you're taking a pH probe out into the field, is there a minimum and maximum temperature recommended?
No, not really, other than the recommended. Normally, I mean, on the Mettler ones, we have a temperature range. So that is what temperature range it'll measure between, and it's normally between 10 degrees and 90 degrees, somewhere like that. So, for example, you'd struggle to use it in the Arctic if you're outside in the Arctic or Antarctic. And obviously you need to keep the electrode warm before you take the measurements in ice and very cold solutions. But generally, if you try and keep it at room temperature when you're not using it, then that's the best thing.
Aurelie asking you about if we do a linear calibration for a buffer at pH 8, is it more accurate to use only 2-point calibration solutions, pH 7 and pH 10, than to do a 3-point calibration using the pH 4 also?
Yeah. So the answer to that one is technically it would be it would offer the same type of accuracy if you did a 2-point versus a segmented one. But it depends on the meter you're using. So some meters you can't do segmented readings, and therefore it's something you need to look at on your meter. Like I say, we recommend to do more points, the more accurate it is. But in your lab, it might be that the accuracy you're getting between doing a 10 and a 7 is perfectly fine, and you accept that, and that's great, and not a problem. But maybe you want to check it out one day and do a measurement of 4 and calibration at 3 points and see if that changes the accuracy somewhat. And if it doesn't, then carry on doing what you're doing right now. That's fine.
Yep. And then we have from Sophia, if the slope is fine, but the offset is getting higher than slope 99.5% offset minus 12.5 millivolt, is there something that can be done, or is it just to change electrodes?
If I remember correctly, I don't think anything needs changing with that electrode.
No, I was also thinking that it
so if I go back,
perfect.
I think I did it. There we go. So you can see a slope of 99.5 and an offset of minus 12.5 millivolts is absolutely perfect. The sensor's in good condition. So in that case, you don't need to change or do anything there. It's only when it gets plus or minus 20 millivolts or plus or minus 5%, not 0.5%, but 5%, does that need changing or looking at. So what you've written there, if that is correct, then your electrode is absolutely perfect and in great condition.
Yeah. I think it was the last question for you today. So thank you very much for this informative webinar. It was very interesting, and I'm sure our participants enjoyed it as well. As this was the last question, I would now hand over to you, Tina, to conclude the webinar.
Thank you, Eva. Yes, I have to say it was really interesting, amazing session. Before we finish, I would like to thank you all once again for joining us. And of course, a special thank you to our speaker, Scott, for delivering such an engaging and informative session. Before we say goodbye, just a quick reminder to check our website for upcoming webinars. And if you would like to stay informed about the latest news and future sessions, please follow us on our social media channels. Wishing you a great afternoon, and until next time, goodbye for now.
Goodbye.
Bye-bye.